Hello, everyone, and thank you for joining us for today's webinar, Supercharge Your Solids and Turbidity Measurements. I'm Heather Masaccio, your host from Water Online. With me today, I have Carlos Williams, Process Application Specialist, Steve Myers, Application Specialist Manager, Eric Lehman, Sales Development Manager Industrial, and Brad Connecticus, Vertical Marketing Manager, all with Hach. Now, in this webinar, our presenters will discuss how you can use cutting-edge solutions to help meet your compliance needs and optimize your water quality processes. After the presentation, we'll be holding a live Q&A session. Feel free to submit questions as we go along. We'll get to as many as possible during the event, and any that we can't get to, we will follow up with post-event. Now, if you run into any issues, please try refreshing your browser first. And if you need additional support, go ahead and submit a question via the Q&A, and I'll get you back on track. Finally, the webinar will be available for on-demand viewing. You'll receive a link via email as soon as it's available. Now, with all that said, I'm going to turn it over to Bradley to get us started. Bradley?
I will be functioning as host for today's presentation. While today's content is delivered in the English language, I would like to acknowledge we have registrants from over 40 countries all over the globe. We sincerely appreciate the investment of your time, particularly if it is outside of your normal working hours. And now on to our key learning objectives. We hope you leave today's webinar with perspective on the following learning objectives. First, how total suspended solids, or TSS measurement, is used in water quality management and the value of reliable data. Second, how to understand the differences between turbidity and TSS, as well as the relevant measurement methods and solutions. And finally, some working knowledge of application case studies related to TSS measurement and the equipment solutions which enable the results. In addition to these learning objectives, I would like to set expectation that we will primarily focus on total suspended solids methods and applications. We do address turbidity and TDS briefly from a differentiation standpoint, but will not be focusing on methods and applications in this presentation. Much of the focus is on line TSS methods used in process control. That said, in reading the comments our audience provided during registration, summarized in this word cloud, we have noted there is an interest in a deeper focus on turbidity methods and applications. We will plan our future content accordingly and appreciate the engagement and feedback. And now a little bit about Hach. Our vision is to make water analysis better, faster, simpler, greener, and more informative via unsurpassed customer partnerships, the most knowledgeable experts, and reliable, easy-to-use solutions. Starting with the founding of Longa in 1933 and Hach in 1947, our company has over 90 years of pioneering new techniques for water analysis, including more US EPA-approved analytical methods than anyone else. Our expertise is in municipal and industrial markets, both of which are represented on today's call. We have manufacturing and, I advanced a little early there. We have manufacturing and engineering locations in the United States, Germany, France, Switzerland, and China. We have over 3,900 employees worldwide and the largest direct sales and service force in our industry. We are present in more than 40 countries and complemented by representatives or distribution partners in an additional 50 countries. In the lower right, excuse me, and now for just a quick overview of our water quality analytical solutions. You'll see we have both laboratory, field, and portable equipment, as well as process and online solutions. In the lower right-hand side of the slide, we are displaying our Solitex and TU5 equipment, both of which employ the light scatter techniques we'll explore in this presentation. If you have not been to our website lately, we encourage you to visit and see details of our current and featured promotions, as well as other valuable water quality education and training content. The site has a self-serve e-commerce storefront with a hierarchical search function to help you get relevant resources as quickly as possible. It's now my privilege to introduce our session presenters. From the left, Carlos Williams has served in the analytical chemistry, online monitoring, and laboratory analysis fields for over 20 years. He studied molecular biology and biochemistry and has lectured on water analysis to help municipal and industrial organizations analyze their data and improve processes. Steve Myers brings a vast range of experience in the water treatment industry, working in multiple roles in the water treatment field. Steve holds a Bachelor of Science degree in Civil and Environmental Engineering and is specialized in implementing strategic programs, wastewater treatment, and water treatment facility construction. Eric Lehman is a chemist who brings over 20 years of experience and serves as one of Hach's sales development managers, where he has demonstrated a history of analytical instrument knowledge, operations, and environmental awareness. I am a vertical market manager focused on Hach's industrial segments in North America. I've served in the industrial water solutions space for over 11 years, including treatment, monitoring, and analytics segments. Before handing off to our first presenter, I'd like to set context for today's focus on total suspended solids. Many of us are familiar with the National Pollutant Discharge Elimination System, or NPDES, which governs discharges from a point source into the waters of the United States. Other nations have similar systems. The information shown here comes from Global Water Intelligence, in which they analyze NPDES discharge permit exceedances in 2022. Of over 23,000 permits, about 10% incurred some kind of pollutant exceedance in that year. On the left side, the data is broken down by state as well as by pollutant type. You will note that TSS is the top parameter in exceedance, representing almost 4 times as many exceedances as the next most frequently exceeded parameter, BOD. On the right side is a breakdown of permit exceedances by industry, with nearly 50% of violations associated with food, beverage, and chemical processing facilities. Eric will detail application scenarios relevant to these types of facilities later in the presentation. And now I'd like to touch on a little bit of more detail on how small particles like TSS lead to large expenses. Without proper monitoring and treatment, let's take a look at how an industrial facility can quickly accumulate expensive monthly surcharges on top of compliance fees. Consider a facility that processes 1 million gallons per day and is routinely operating 20% over their TSS limit. This volume is what you might see at a large manufacturing operation, such as a specialty dairy. This would be about 1.5 tons per month of solids in excess of the permit limit. If the municipal public works is assessing a surcharge of 50 cents per pound, this trend results in 72,000 annually on TSS-related surcharges. I have personally worked with industrial clients for which this figure was as high as 250,000 annually. In this scenario, there could be the cornerstone of a business case to implement additional on-site treatment, such as dissolved air flotation, to eliminate the surcharge burden. While this scenario represents this as a cost optimization story, in other scenarios, there may be a utility in ensuring a certain minimum target volume of biomass is consistently sent from the industrial facility to the municipal public works to ensure the public works is balanced, i.e. keep the bugs happy. In both cases, reliable and accurate TSS measurement, both online and offline, are extremely important to the relationship between industrial facilities, municipal public works, as well as the watersheds and communities they operate in. I'll now pass over the presentation over to Carlos Williams to address methods for solids measurement. Carlos?
Good morning, good afternoon for anyone that may be in the afternoon. Thanks everyone for visiting us from around the world. My name's Carlos Williams, as Brad said, and I'm going to talk a little bit about turbidity as it pertains to other types of solids. So I won't read this entire table to you, but the intent to show you here is that we are going to connect how we measure total suspended solids, which is a commonly performed lab parameter, over to how we measure it online, which uses the fundamentals of turbidity. So as you can see in these first 2 columns on the left-hand side, we've got turbidity in FNU, which stands for formation nephelometric units, and in NTU, which is nephelometric turbidity units. In terms of the mathematics between the two, there's no conversion factor between the two. Really, what they end up doing is their equivalent. What they are is they define which method is being used to measure turbidity. And both of these can be used to measure online TSS. So what we see, if you look down in this this third row where we're looking at offline and online. So under FNU, the FNU uses a light source at 860 nanometers, and that conforms to the ISO method for turbidity reporting, ISO 7027. And then in the second column, the NTU values conform to the EPA method 180.1. And if you'll notice, the major difference is that there is infrared light, which is essentially colorblind for the ISO method, and then we have light in the visible spectrum for the EPA method. Then if we move over to total suspended solids, we're no longer measuring in nephelometric turbidity units or formazin nephelometric units. We're measuring in milligrams per liter of solids. So just note that in this green box right here, the nephelometric units or the formazin nephelometric units are very fast. They're very easy to do online, but they're not a direct measurement of total suspended solids. But what we'll talk about as we go through these slides is that there's pretty easy ways to correlate the two things. And then there were questions about from the registrants about total suspended solids versus total dissolved solids. So total suspended solids, and I think we talk about this in a little bit more detail, but suspended solids are basically the things that are left over when you filter a sample, and total dissolved solids are things that make it their way through the sample. They get collected on a pan, and that pan gets dried, and then in both cases, you either weigh the filter or you weigh the pan. And total dissolved solids, the online measurement, again, is not a direct measurement using a scale and drawing a sample, but it uses electronic conductivity. So you're not meant to be able to read this text. If you can, good on you. Your eyes are better than mine. But this is basically all the steps it takes to go through a standard gravimetric analysis. Essentially what you do, I kind of sketched it out already. You filter a sample, you filter a certain volume, you make sure that the filter element has been dried in an oven, then you make sure you have you have a constant weight once you dry it down. Then you measure the difference between the dry filter that doesn't have any solids collected on it, and then after the solids have been collected on it and dried. So there's a lot of steps to it. This is the entire point. And this is why measuring something online for total suspended solids is a lot better and a lot easier. So an inline alternative that folks are going to talk a lot more about, this is a TSSSC or a Solitax. This is a probe you can use to measure online. A little bit about the theory of light scattering. So when we use a nephelometer, one of the key components of a nephelometer is something that measures at 90 degrees. And so what these images are showing you is when light scatters at 90 degrees, when you see over here on the far left side, you get a pretty equal distribution of light scatter. At least it's equal in these two lobes you see on either side. Then as you move to different means of scattering, or as the particles get larger and larger and larger, or both, then you start seeing these very strange patterns of light scatter, which is why a lot of the TSS measuring technologies will have within them at least one detector that measures at 90 degrees, and then depending on the instrument that you're using, may have more than that. So here again, you've got this is one design of a traditional nephelometer. So you've got a lamp, a lens, you've got a sample cell. So if you're using an online measurement, you won't necessarily have a sample cell, and you may have other detectors. So you may have one at 90 degrees, you may have one at 180 degrees or at 45 degrees. And then in some cases, you'll have a transmitted light detector as well, because the transmitted light is something that if we can, it'd be nice to account for, because when we have a sample that has not only turbidity but color in it, the color will absorb some of the wavelengths of light. So if we can compensate for that using a transmitted light detector, that's what we like to do. The transmitted light detector is typically something that we find on lab instruments and not on process instruments, but it's a handy tool to have. So here's another method of the 360 by 90 nephelometry. So the goal here, and this is some of you may be familiar with Hach equipment. This is the basis of the TU5 series. So process analyzers are TU5400, TU5300, then the lab analyzers are TU5200. This was called the donut when we first designed it because it scatters light in 360 degrees and collects light in 360 degrees. And that 360 degree light detector picks up scattered light at a 90-degree angle. So once again, it works as a nephelometer. So just one word about, you guys are going to hear my colleagues talk a lot more about correlating solids and turbidity, but this is an important thing to remember because what I have here are two sample cells that have a few very large particles and then another sample cell that has a lot of small particles. And so when you could have something that measured by turbidity will scatter the same amount of light, and so it will give you the same turbidity value. However, if you're trying to do a suspended solids value, those two might be completely different. And the point being is that if you think that that your sample stream is going to be highly variable, or there's going to be times of the year or times in a certain process or something like that where you see differences in the suspended solids measurement or in the turbidity measurement, it's always good to at least verify, if not calibrate, your turbidity device that you're using to measure suspended solids. So I think with that, I'm going to be handing it over to Steve. It's all yours, Steve.
Awesome. Thanks, Carlos, and thanks, Brad, for kicking it off, and thanks to the attendees as well. So I'm going to jump in and sort of to build upon what Brad started out with in the presentation about how turbidity can be suspended solids can be an exceedance in the effluent. I'm going to talk a little bit about how we want to use suspended solids measurements in the process. So we're going to be talking about this through a wastewater treatment process here. And so I have a little colorful dots here, essentially showing some of the common locations where you might want to keep an eye on your suspended solids. So first off would be the influent. This is where we have the waste stream coming in. Second would be in those aeration tanks where we have the biological treatment. So we're going to be focusing on biological treatment here. Third would be in the liquid solid separation. So here we show a clarifier, but that could be also filters or other ways to get the solids and water separate from each other. In the clarifier sense, we'd have the underflow, which would be the waste or the return sludge that's going back into the biological treatment for solids processing, maybe the underdrain from a primary clarifier as well. And then finally going on the way out the plant, this is again where the compliance point would be. But we're going to talk about how solids impacts process decision-making. So biological process decision-making to be specific. So here's a few parameters on the side here that sort of are pretty important for monitoring and optimizing your wastewater treatment system. So the first one I'll talk about, well, the first and last one sort of linked together, is your return activated sludge and your waste activated sludge. So this will be the amount of solids that you're bringing back into or keeping back in the process. So mixed liquor concentration, which can be represented with suspended solids measurement, is one of those. The waste activated sludge, that would be essentially how much you're wasting out of the process. That's a really important parameter. Both of those have a big impact on the treatment stability. The food to microorganism ratio, this would be, this is a pretty important parameter where we're actually monitoring how much biomass is in the system relative to the amount of food, in this case BOD, coming in. That has important implications on how fast biological treatment reactions, or kinetic rates as we refer to them, are taking place, so where optimization lives. SRT is one I'll talk on a bit more detail in the next one, but this one essentially takes into account the mixed liquor suspended solids, so TSS, if you will, as a correlation there. In the aeration tank, how much biomass is in there relative to how much you're getting rid of on a regular basis. This is essentially, we'll get into more details on the next slide. And then the sludge volume index. So this would be a representative measurement for how fast solids are settling in the clarifier. If you're doing filtration for liquid solid separation, you may not be too concerned about this one, but absolutely you're concerned about this one if there is a liquid solid separation by gravity. How fast is that solids actually settling down. So double clicking a little bit on sludge retention time. So this is a really important process control parameter. And it's, again, a slide where it might be a little bit difficult to read here, but on the left, on the blue graph, you'll see on the vertical axis, we have the SRT in days. And on the bottom horizontal axis, we have the temperature. And what we're essentially showing here is that if you have a system, and this is for nitrifying systems. So if you have a system with nitrification as part of the design, or not actually, in a biological process, you will want to know what your solids retention time is to best optimize for your process. And what we see here is if you have a very warm temperature, you can get away with a pretty low solids retention time. Whereas if you have a cold temperatures, and this is of the water, those bacteria are going to slow way down, and you'll need a lot more time for them to do their job in the system. Conversely, if you're trying to avoid nitrification, you may find that this is also insightful for how short of an SRT you want, so you're not accidentally growing some bacteria that are going to have a significant impact on your aeration demand. On the right side, you'll see here a graph showing the relative population amounts of certain bacteria and microorganisms in the water, going from a low to ideal to high SRT system. Ideal being sort of that Goldilocks zone. And what we find here is that if you don't have ideal optimization of that SRT, again, SRT stands for sludge retention time, and it effectively represents the length of time that a bug lives in your system. So suspended solids measurement in the process is effectively measuring your workers, your bacteria that are taking care of the treatment process for you in real time. And if you have too long of an SRT or too short, long, high or low, you can get to a point where you have pin flock, poor settleability, poor treatment. And then we also have a few relative populations of indicator organisms also shown on the graph there. Moving on. As far as the accuracy of the SRT, there's a lot of benefits that have been demonstrated to have a very accurate understanding of your SRT. So again, that calculation takes into account the suspended solids measurement. And if you have an accurate understanding of it and your targets are set right, you can increase your secondary treatment system capacity by 30% or more versus a moderate or poorly optimized system. Your aeration efficiency and the amount of air you're going to need in your process can absolutely be reduced with optimization of SRT here. Your settleability, as I mentioned before, if I go back one slide, one of the issues that we can get, well, actually it's coming up on this slide, on the fourth bullet point there is filaments will grow. These are specialized bacteria that essentially are like stringy in nature, and they sort of act as parachutes for bugs where they're trying to settle. So your settleability is negatively impacted by having these in there. And if you have an unoptimized system as it relates to your bug life or your SRT, you can find that will be a major impact in your process. Also, nutrient removal, if you're looking at biological phosphorus removal or ammonia nitrate reduction in your system, those can all be negatively impacted without having proper SRT control. And of course, the solids yield and growth rates are also impacted. So lots of benefits to looking at this. Here's a quick example of just the advantages of keeping a close eye on solids in your system. So this is a wastewater treatment plant not too far from me where they have a primary clarification feeding the aeration tanks here in a collector, essentially a distribution point that distributes the sludge and the influent between the 4 aeration tanks. And then they all collectively gather in this effluent channel, and this treatment plant was measuring at this outfall, which was sort of a collection of all of the treatment processes. And they were noticing that they were having some struggles when it comes to ammonia removal. And they didn't quite know exactly what the issue was. So they went in these smaller circles here. These will represent essentially where they did some grab samples to take a look and see what's going on in our process. Now this slide, a little bit to unpack here, but on the top we have vials, some of our test and tube vials for ammonia measurements. The yellow represents a low amount of ammonia in the water, and green over here represents a higher amount of ammonia in the water. And these all represent each one of those 4 aeration basins. And down below, each of these settleometers correlate to one of the vials above. So we can see them going from left to right. What they found here is that on one of those aeration tanks, they were getting a higher amount of ammonia going through. And then when they evaluated the solids, now the settleometers here are for measuring the SVI, so it's not necessarily exactly right, but what we can see here is a lot lower amount of solids versus some of these other settleometers in one of the basins. And effectively, what they were able to deduce from this is they had an unequal distribution in this channel of solids to each of these aeration basins. So that mixed liquor that's coming in there was not evenly split between the 4 aeration tanks, and one of those poorly functioning tanks, because it didn't have the amount of solids it needed, was underperforming when it came to that ammonia reduction. And so found that at high loading times they were struggling, and as a result of this, they decided, you know what, we're going to put some online monitoring in there, and we're going to measure solids in each of those locations, each of those aeration tanks independently, so that they could counteract this issue going forward, at least know when they're getting clogs or blockages in those distribution lines or an uneven split through the process. The last thing I want to talk about is that mixed liquor, even though we can, and the suspended solids concentration in these processes, it's quite dynamic. This is a 24-hour period, and you can see the waste-activated sludge does change quite a bit throughout the day, as well as that mixed liquor activated sludge, or the mixed liquor suspended solids does change quite a bit throughout the day. So this begs the question of, what is the best time to, if you're going to make these calculations, these critical calculations for SRT and other process optimization parameters, when is the best time to pull that sample for the grab sample? Or would it make sense to take a look at the entire day together? So just like you're picking stocks at the stock market, and it's tough to time the market, it is rather challenging to also time when to take that grab sample to be actually representative of the solids in your system. Again, here's another activated sludge mixed liquor concentration. You can see it going quite a bit, drastic changes from over 3,000 milligrams per liter down to near 2,000 milligrams per liter, all through the course of a single day. So about a 30 to 40% swing through this diurnal change. So when do you take that grab sample? And that's the question that needs to be asked here. And what we're arguing for is that there's an opportunity to get a better view into your process control and optimization by looking at your process in real time, in addition to taking those grab samples as well. Now I'll turn the rest of this to Eric to talk a little bit about some of the specific solutions that can help with this.
Great, thank you, Steve. So in the next few sections, we're going to be talking specifically about the technology and the sensors that we use to measure TSS and or turbidity. So on this slide, you can see we have a number of different options, really depending on the application you're trying to measure the turbidity or TSS in. But for this section, we're going to focus specifically on the Solitax and the TSS as pictured in this box here. So as Steve mentioned, there's a number of different applications where we would want to monitor turbidity or TSS. In industrial water, we'll mention a DAF here in the next few slides. Maybe there's a high temperature application, high pressure. If it's a refinery or a chemical plant, there might be a class 1 Div 2 requirement, hazardous type environment where we need to be aware of. So there's a number of different applications we would actually want to use a turbidimeter or TSS probe to measure real time or in line. So we have two different options when it comes to probes. In 1995, it came out the Solitax SC, which is really designed for municipal type applications. It has a quartz detector window. In 2009, we came out with the TSS SC, which is really designed more for harsh applications, more industrial type applications. Has a sapphire detector window, so definitely a harder type material than the quartz. So again, it really kind of comes down to what application you're trying to measure your solids or TSS in. I love these pictures here. It really shows the effectiveness of the wipers on the probes themselves. So there's a self-cleaning wiper, there's a built-in humidity sensor, and then multiple detectors, which we'll get into here. So the principle of operation, how are we actually detecting turbidity or TSS using a probe? So we do use LED light sources to transmit the light. The Solitax uses a 45-degree light at the sensor face, uses a 90-degree transmitter light beam, and then 140-degree transmitter light beam to detect the actual scatter of the light. The TSSC actually uses 2 pulsating infrared lights and then has 4 receivers versus the 2 receivers of the Solitax. Some things to point out here is it does have integrated bubble and temperature compensation software. So to a degree, it will compensate for bubbles. However, of course, we wouldn't want to install, let's say, an aeration basin above a diffuser or some sort of blowers. So keep that in mind. Another thing too is it is color independent. So if there's color in the sample, that will not affect the readings of the probes themselves. So Carlos had mentioned previously the gravimetric lab procedure where you're weighing out the filter, you put it in an oven, you dry it out, and that's your gravimetric lab procedure. What we do for the calibration of the TSS probe is we pull a grab sample right next to the probe that's mounted in line. We'll capture that value on the sensor itself, take that sample to the lab and determine what the gravimetric TSS result is. And then what we can do that allows us to enter a factor into the probe. So now we're taking your sample, your matrix, determining the TSS value, and then entering that factor into the probe. So that's how we get the TSS rating versus just a single point NTU calibration. We have a couple of different mounting options for these probes. So this specifically is for the TSS probe, a TSS-SC probe. On the far left-hand side is more of our insertion mounts. So you can see we have a ball valve up top there. So a ball valve mount right there. So easy installation. In the middle, we have more of what's called a safety armature. So more for high pressure applications, 87 PSI and below. And then the far right-hand side is the immersion mount. So if you're mounting this into maybe an aeration basin or some sort of tank. This is specific to the Solitax probe. So we have the immersion mount, similar to the TSSC. We have the higher pressure safety armature, and then the another safety type armature that really is for low pressure type applications. So again, it depends on where you're going to be installing these probes, what the application is. Just make sure we're choosing or selecting the right mounting configuration for that requirement. A great picture of some installations from some of our customers. Far left-hand side was in a pulp and paper plant, paper mill. Again, pretty aggressive applications. Up top there is the insertion type mounts and then the ball valve mounts. Some basic maintenance for the probes. Of course, it does have a wiper similar to the windshield on your windshield wiper on your vehicle. That does need to be replaced every so often, about every 20,000 wipes or 20,000 cycles. So fairly easy to maintain. Some of the more advanced maintenance, there are some seals inside the probe that need to be replaced about every 2 years or so. There's a desiccant inside to prevent any sort of moisture being built up. So there will be some maintenance involved for these probes, but very minimal. So let's get into some examples of where these are used. So the first example is in an industrial application. Oftentimes they use what's called a dissolved air flotation tank or piece of equipment, or otherwise known as a DAF. A lot of times that is used to remove fog, your fats, oil, and greases, your suspended solids, and to a certain extent, your BOD or biological oxygen demand. So this is a typical view of what that DAF is going to look like. When it comes to control aspects of a DAF, there's a few things to consider. First is your solids loading rate. So how many solids or how much solids are coming into that tank to be processed or treated. There's the hydraulic loading rate. So how much flow is actually coming into the tank, which both need to be controlled to really ensure that you're having good quality effluent coming out of the DAF itself. Regular testing. So if you do have a DAF, how are you controlling that? Is it simple grab samples? Is it visual management? Or is it inline probes to help you automate that process, which we'll talk about here shortly? So yeah, maybe you're using inline probes, pH, TSS probes, etc. Chemical usage. So oftentimes chemicals are dosed at this point in the process. So whether it's a flocculant or a coagulant that's being added to it to bring these, create larger particles to have some float up and be skimmed off, or settle to the bottom, which can be captured as more of a cake or a sludge cake. So typical operation. This is fairly typical. Going into a lot of plants, industrial plants, there's an overloaded system, which means they're really trying to push their system because they're trying to get as much treatment as possible, which can lead to a number of different problems. Lack of understanding of the process conditions. Because their process is so dynamic, it's difficult to control and really understand, if they're overloading, if they're adding too much chemical or too little chemical. And then of course, there's usually one operator, Bob, that knows the DAF inside and out. But when he's on vacation, who's going to run that DAF? Who operates that DAF? So that can be problematic. Maybe there's a manual approach or a visual management where they're looking at just visually looking at the effluent quality. The back 1/3 of the DAF, that's where it should be accumulating that sludge cake, and just really visually seeing that, hey, this is healthy or it's not, meaning that maybe we need to increase our chemical dosing or decrease it. So this is an example, real life example of what it looks like, to manage or control a DAF using grab samples. So if I can point out a few, so the dots here, so on the bottom line, the blue is going to be the filtrate or the effluent. The top line is going to be the influent. And then the dotted lines are just the kind of the baselines or the typical operation of the DAF itself. The dots here are going to be the grab sampling points. So if we look at this one here and here, we can see as they pull the grab sample, it looks like everything's in check and it's operating as expected below the baseline. But just after that grab sample, we can see that something happens. We can see the influent TSS, or the TSS starts spiking, which means the effluent starts spiking. But then by the time we pull that next grab sample, everything looks to be back in normal capacity. But when it's spiked like that, or when you have that upset, it could mean a violation, right? Or it could mean that you're discharging to the city or to the receiving body of water, where you could be in violation. So the point of this slide is really to show that a grab sample is really just a snapshot of what's going on in your process at that given time. So an automated approach to that would be, on the left-hand side would be your pre-DAF tank. Oftentimes in the industrial side of things, we'll see an EQ tank where they're actually doing some sort of pH control, whether an acid and a base. So they're monitoring pH and temperature at that tank. Coming out of that tank is going to be your TSS, basically going into the DAF. So now we're measuring TSS continuously. So now we can make a determination of, based on TSS, how much floc we need to add, how much coag we need to add. And then so we have more of a feed forward control. You can also measure that TSS on the back end, on the effluent of that DAF tank. So now we can do a feed forward and a feed back control to really optimize that chemical dosing. And then, of course, if you have another DAF running in series, that would be where you could do some more pH adjustments. So this is just kind of a snapshot of how we would automate that process to get real control of our effluent and chemical dosing. So automated chemical dosing really eliminates manual adjustments. So based on the TSS and pH, we can set these set points and have the TSS control, or PLC control, how much chemical we're adding real time as needed. Reduces that operator interaction, so they don't have to check it as often. They're not adjusting the chemical dosing pumps. It's really controlled automatically. So optimizes both the solids and filtrate quality, reduces discharge costs. At the end of the day, we can save chemical costs, and you're consistent in compliance and reducing any type of feeds or overages to municipalities. So it really gives better data, more data, and better control of your process. So at this point, I'll pass it over to Brad to talk about the pulp and paper and fiber loss.
The problem is as follows. We'll zoom in on a client that was a tissue mill in the Southeast United States. They were struggling with high rates of fiber loss and had no capability to understand that loss over time or to associate loss events to individual paper machines. So here's a little bit of context on this industry. Tissue pulp, especially that used in soft and specialty facial tissues, comes from hardwood trees such as eucalyptus, which are grown in tropical climates. In other words, it's an awfully expensive raw material to send out with your wastewater, let alone the sustainability implications if it's left unmanaged. Fiber loss is a key performance indicator of operational efficiency for paper mills. Additionally, water discharge volume restrictions and surcharges for volume in excess of permit allowances significantly influence mill profitability. Projects to reduce water discharge volume and improve efficiency at the mill level can be benchmarked and leveraged enterprise-wide as part of corporate sustainability strategy. So at this mill, they had attempted several different fiber loss measurement strategies, including a recirculation loop, which pumps a continuous sample past a pipe-mounted transmitter. That approach was not reliable due to pump clogs and excessive foam formation, which contributed to inaccurate transmitter readings. Without a reliable measurement strategy, the mill staff was not able to trend fiber loss volume over time and had no means to connect the losses to the individual tissue machines. Excessive fiber loss on the screens in front of the gravity drain resulted in more frequent maintenance actions to remove and dispose, and that involved haul away to landfill, again, a direct production loss. The Hach solution was to install TSS SC probes with the wiper in an immersion mount fashion at points on the effluent side of each tissue machine, as well as directly upstream of the screen in front of the gravity drain. The mill brought those signals into their distributed control system via 4 to 20 analog signals and implemented optimization strategies for each tissue machine based on analysis of peaks in TSS measurements. The continuous measurement allowed excursion traceability to specific tissue machines and events such as spills, production changeovers, maintenance activities, and shift changes. The previous challenge of foam presence and sample line clogs resulted in inaccurate readings. That was avoided due to the TSS sensor's differentiated design features, which enabled reliable measurements even in harsh environments. The results included, first off, the flow to the gravity drain decreased from 75 gallons per minute to 40 gallons per minute. Annually, that's about a 660,000 gallons per year water savings. Additionally, the fiber loss decreased by about 0.2% or half a ton per day, resulting in raw material production losses being reduced and waste haul-off expenses also being reduced. And here are just a couple photos to help with the visual. You can see the tissue machines along this very long trench on the left side. I think that was about 1,000 meters long. And then an example of one of our installations. This is one of our pole mount sensors on the far right of that picture. On the second side, the sensor is actually below that grating, but you can see the cable which leads to the controller and ultimately carries the signal into the distributed control system. So one great example in the pulp and paper industry of how TSS is used. I will now close out some of the main content of the presentation. I'd like to circle back first off to the key objectives. We hope you found this to be a valuable investment of your time and encourage you to contact us with additional questions and your most significant water analysis challenges. The contact section on our website is a great way to get the conversation started with us. Or if you have a relationship with a local representative or channel partner, please contact them directly. This concludes our planned presentation content. We invite you to use the Submit Questions feature. I see there were several that were submitted during the presentation. We'll start with those. And there were also a few questions submitted by attendees during the event registration, which we'll take as well. So Courtney, if you want to take the mic for a second and just help us orient the Q&A section. Thanks,
Sure.
everyone.
Thanks so much, Brad. I appreciate that. And thank you so much for the presentation. As Brad just stated, we do still have time. So if you want to submit a question and haven't yet, you can do so now. Also, please note the related content that is afforded to you on your console. So that's available at your leisure. And a reminder that the event will be available on demand after about 24 to 48 hours. You'll receive a link via email when it's available. So with all that said, let's go ahead and get to some of our questions. And I will start with the first question. That question is asking, what is the relationship between TS, TDS, and TSS? Who can help me with this one?
Carlos, you want to grab that one?
Sure. So TS is total solids, just to define the acronyms. TS, total solids, TDS, total dissolved solids, TSS, total suspended solids. And simply that it's the TS, total solids, is the sum of the TSS plus the TDS. So that's going to be all of the solids that you have in your sample.
Good. Thank you so much, Carlos. So we'll move to our next question. And that question is asking, is Hach's TSS method different than standard method SM 2540? And is it US EPA approved? Who can help me with that one?
Carlos, you want to grab that one as well? It kind of aligns with some of the content you presented.
Yeah. So if you look up standard methods, the standard methods for solids, you will have a lot of different gradations, right? It will talk about suspended solids, it'll talk about dissolved solids, it'll talk about total solids, and it will talk about in generalities about, hey, you need to have a sample that's got somewhere from 2 to 200 milliliters. I may have the number wrong, but it's something like that. It's a pretty wide range. And then it'll just say you have to dry at 103 to 105 degrees Celsius and just dry until it gets to a constant weight. Hach's method is based on the standard methods. It is the US EPA approved method. I think when I've read both side by side, I think there's subtle differences. So I think the Hach method will say, you compared to the standard methods, Hach method will say, dry for an hour, whereas the standard methods will say dry to a constant weight. But truth be told, you need to dry to a constant weight. So if you've dried it for an hour and a half and it still seems like there's more moisture coming off during the drying process, then you need to dry for longer. And there are some of you that may be on this call, there are some utilities that have in their SOP that they have to dry. Maybe they're in a humid environment or something like that, and they'd have to dry for 6 hours or something like that, as opposed to an hour. So some of it is also dependent on what the operator's personal experience is.
Okay, excellent. Thank you so much for that, Carlos. Now moving back to our audience questions, this next question is asking, what is Hach's apparent color, platinum/cobalt test that could be used to perform the AAMI ST108 critical water qualification acceptance criteria? And more generally, how does color relate to solids and turbidity? that you, Steve? Can you help us?
I can take this one.
Good.
This is Brad. So in August of 2023, the Association for the Advancement of Medical Instrumentation, or AAMI, issued standard ST 108 to provide valuable information to the healthcare industry professionals regarding water quality as it pertains to medical device processing. The standard calls for color and turbidity acceptance criteria for all water uses to be colorless, clear, and without sediment. So Hach does have a platinum cobalt standard method. It's a method 8025, and that is equivalent to the National Council for Air and Stream Improvement Method 253. We performed that method on our spectrophotometer equipment, and that would give you that, using that method, you'd be able to ensure that water quality was colorless, clear, and without sediment in accordance with that standard.
Okay, very good. Thank you so much, Bradley. Okay, back to our question. So the next question is asking, can I use a field colorimeter to test suspended solids? What are the advantages or disadvantages of this approach? How about this one?
So I can take that one. So we do not recommend using a colorimeter or spectrophotometer for TSS. The colorimeter is really a piece of equipment that is set a specific wavelength, looking for transmittance and absorbance. It's not necessarily looking for backscatter. In fact, we have a lot of operators that try to use a little colorimeter for turbidity. It's not a good indication for TSS or turbidity. It's really meant for determination of a specific parameter, say chlorine or something like that, where it's reacting to a reagent and turning a color. So we do recommend specifically using, if you need a portable turbidimeter, we do sell portable turbidimeters. Suspended solids, we do have a probe that you can drop in that's more portable. But no, we do not recommend using a spectrophotometer or colorimeter for TSS or turbidity.
Okay, excellent. Thanks, Eric. So next question that came in, let's see. What are the maximum minimum TSS readings for those meters and accuracy? Who can help me with that? And again, it's asking, what are the max minimum TSS readings for those
mine.
meters?
I'm happy to take that one. So yeah, this is a question I'm going to answer from a functional standpoint, just from what I've observed in the real world. So I've been at activated sludge treatment systems where they're using Solitax or the TSS sensor for inlet water TSS for the activated sludge. So that would be like 200 to 300 milligrams per liter for the inlet. Activated sludge tank, which would be 4,000 to 5,000 milligrams per liter. And even on the effluent or on the effluent, which would be down to 10, and sometimes less than that milligrams per liter, and on solids management systems where we have like a thickened stream of solids, maybe going up to 3 to 5%. I would say functionally, you can get down to the single digits. It's going to be plus or minus, maybe 5% or a little bit more on the low end. As you get up to the higher end, I'd say functionally, you'd probably be maxing out around 5 to 8% solid. So that's going to correspond with about 50 to 80,000 milligrams per liter. If you're going to be much more than that, then there might be a different technology worth looking at. But for these optical sensors, they do pretty well within that entire range with a good calibration. And by good calibration, what we're looking at here is essentially as described with these sensors, you want to take a grab sample and sort of tell the sensor what it's seeing. And once you've established that, and as long as the solids characteristics in the water don't drastically change your process shifts, you may want to do another grab sample in comparison. I'd recommend for stable systems, still checking that probably monthly. Maybe a couple times a month wouldn't hurt. That's probably the main range that we're looking at. I would also say, though, there will be a bit of a difference between the Solitax and the TSS-SC, with the TSS-SC working a bit better when we have higher concentrations of grease or fog, so fats, oils, and grease. maybe coagulants as well in the water, it does a bit better with the multiple emitters and detectors. But for, I'd say 80 to 90% of all of this online measurements that you'd want to have in a typical activated sludge treatment system, as well as many industrial systems. I've seen these work well in carbon fiber production, in food, poultry, all sorts of applications. So pretty wide range of measurement value that you can look at. And the accuracy, I'd say, is plus or minus 5% with a good calibration to sort of put a pin on it.
Okay.
And one more
ahead.
thing to add there too. So with these probes, we can do multiple point calibrations. So if you have a system that is dynamic and changes frequently, you can do a calibration where maybe your system is stable, and then do another calibration where you might have an upset. So you can do a 3-point calibration really to build that linear correlation and have greater accuracy that way too. So there's a 1-point calibration option and then multiple point, really, again, depending on your process and application.
Okay, excellent. Thanks to both of you. Now we have a question from Brian, and he's asking a question regarding turbidity, NTU versus FNU. The question is asking, can NTU standards be used to calibrate a meter recording in FNU, or would this result in an inaccurate reading? Who can help with this one?
Yeah, I can help with that. So really, this is the FNU and the NTU are a little bit of, as we say in English, tomato. There's what they, in terms of the measurement and what kind of standards you would use, you could use the same thing. So if you have a turbidity standard that says it's 20 nephelometric turbidity units, that will also correlate to 20 formation nephelometric units. The only reason that we have that is because of the different light sources. And so when we're using standards, it doesn't really matter because it's just measuring light scatter. However, when you are actually measuring in a sample, sometimes it's good to know whether something has been measured in formation nephelometric units, because color doesn't impact the instrumentation that uses an infrared light source, because it's essentially colorblind. And whereas the nephelometric turbidity units instruments that comply with things like method 180.1 for turbidity measurement use a white light source that emits light in the visible spectrum. And so color may impact that. So it's just a way for people to know that this measurement was done with one type of instrument versus the other, but you can calibrate them with the standards that you use wouldn't matter.
Excellent. Thank you so much. I think we have time for one more question. And this question is asking, do these work on primary sludge, like 4 to 8%? Does Hach cover a microwave technology or TS like Serlic? I'm hoping I asked that properly. Who can help me out with this question?
Maybe Eric and I can tag team that one again. But in terms of the primary sludge, what we've found is the TSS SC does work better in primary sludge versus the Solitax due to, like I mentioned before, the higher content of fog that might be making its way into that stream. Eric, do you have any thoughts on that one?
Yeah, absolutely. So sludge thickening, sludge dewatering, we have installations where we do use that sensor to control maybe a polymer. But as far as the microwave technology for total solids, usually that's used for grab samples. There's a brand out there called O-House, where basically you drop a known amount of sample into this little microwave looking thing. It dries it out, does a calculation for you, and reads out what your total solids value is. We don't manufacture one like that. We do resell one, manufacturer, a microwave technology. I think that's what the question's kind of alluding to there. So it is more of a grab sample microwave.
Okay, very good. Well, I think that is our time for today. I want to thank Bradley, Carlos, Eric, and Steve, our presenters, for this wonderful presentation and for sharing their time. And I want to thank you, the audience. If we did not get to your question, no worries. Our presenters will be responding to you post-event. And that's our show. Have a wonderful day, and we'll see you next time. Bye-bye.